Last time we were talking about equivalence, right? Basically the concept of an equivalent as the measure of charge rather than concentration of charges rather than concentration of individual ions. And we mentioned that equivalents are fairly often used in medicine when the concentrations of critical ions are expressed in the equivalence rather than the actual concentration. So this just shows you what are the main ions in the IV solutions, but now we're going to kind of refresh our understanding of the equivalence here. So in 1 mole of iron 3+.
Actually, that's what I remember at the end last Wednesday. I was thinking of a table that I was asking if it's going to be on, if we're going to have a reference. Is
this?
Yeah, like the soluble, like which ones are soluble.
Okay,
which ones aren't.
Solubility. So we're going to get back to the solubility of compounds, but yes, you will have to know the broad rules of solubility. Okay? So 1 mole of iron 3+ contains how many equivalents? 3 equivalents, yes. Just a reminder, 1 equivalent is the same as 1 mole of charges. So if you have 1 mole of iron and each iron ion has 3 charges, that gives you 3 equivalents. This 2.5 moles of sulfate ions. How many equivalents do we have? 5, yes, because we multiply the number of moles by the charge. And if we have sodium chloride in a bottle and there are 35 milli equivalents of sodium, how many milli equivalents of chloride can you expect in the same bottle? Go ahead. 34, yes. Okay. Good, everyone? Any questions on this? So pretty much we're going to be answering Zach's question about the solubility rules. So solubility in quantitative terms here, it's the maximum amount of solute that dissolves, as you can imagine, in a certain volume. Okay? So this parameter depends on the temperature. Generally speaking, solubility increases with temperature for salts. It may be increasing to a different extent, but usually it does. When we compare solubilities, we have to use uniform units. And these uniform units are specifically grams of solute per 100 grams of water. So imagine that you are adding a solute. For simplicity, let's talk about sodium chloride to the solvent, water. When you start adding sodium chloride, all of it completely dissolves in solvent, in water. Okay? You keep adding, it keeps dissolving. The solution which can dissolve more solute is called unsaturated. When you reach the point where solute does not dissolve anymore and just remains at the bottom of your vessel, we're talking about saturated solutions. So a saturated solution maximum amount of solute that can dissolve. An example of naturally saturated solution actually is, I think we mentioned, maybe we did, maybe we didn't, a Dead Sea in Israel. Because the solution is so concentrated, so saturated, that the floor of that lake is covered with salt. Okay? And I want you to appreciate that this is a very important note here, right here. When you have a solute at the bottom of the beaker with saturated solution, it's not like, you can clearly differentiate between the ions that are in the solution and the ions that form the actual solute, the actual precipitate. As some of them dissolve, others recrystallize. So it is ongoing equilibrium process. Okay? Good? I hope it makes sense. Okay? So, if you add salt and to water and it disappears, what you get? Saturated or unsaturated solution? Unsaturated. But then you keep adding sugar and it never, at some point it stops dissolving, so we have saturated, right? Good. So that's the solution, and here. So this is a very interesting conversation we're going to have. So this is the solubility of potassium bromide. Okay. My suggestion, when you study, when you talk about these things, you can easily get bogged down with sort of mathematics part of chemistry. But chemistry is not about math, it's about chemistry. So you need to think, okay, what does that mean? And what it means is that 80 grams of potassium bromide, right, can dissolve maximum, no more than 80 grams of potassium bromide can be dissolved in 100 grams of water. Clear? So question number 1. This 60 per 100, saturated or unsaturated? What do you think? Well, can you explain why it's unsaturated? Yes, because it's not the maximum amount. It can be dissolved in 100 grams. Okay? What about number 2?
Saturated.
Saturated. Why do you think so?
Because it's over 80 grams. So if 80 grams.
Yes.
Is there a difference really between, because I remember last semester I heard a term called supersaturated. Is that, because wouldn't that like 200 be like supersaturated?
Okay, let's finish this. I'm going to quickly speak about supersaturated, okay? And then I'll answer your question. But basically how you come to that conclusion, if 80 grams can be dissolved in 100, then 160 can be dissolved in 200, right? And in this case, 160 grams is is the smaller amount, whatever, than 200 shown here. Okay? What about the bottom one? Unsaturated, because if it's 25 in a 50, it's going to be 50 in 100. Okay? Any questions on the concept of solubility, saturated or unsaturated solutions? Okay. I'm going to skip the solution. So this is it. Effect of temperature, solubility. You can see that the behavior is very different, right? Does that make sense? So for instance, for sodium chloride, there's practically no difference. So it is limited at roughly 40 grams per 100 grams of water. Okay? Does that make sense? For the most part, they increase fairly steeply. I really want to highlight glucose. Okay? Hear me out. So let's take a look at the solubility of glucose at the temperature of 20 Celsius. Pretty much room temperature. Okay? We can assume that it's pretty close to 80 grams per 100 grams of water. Am I making sense? Now let's take a look at the temperature of, well, let's say this. Okay? The solubility of sugar, well, not sugar, it's glucose, but close enough, will be 200 grams per 100 gram of water. If you ever made a syrup, this is how you make it. Okay? Does that make sense to you? So now one thing that I want to highlight for you and attract your attention to. So for most solids, for our intents and purposes, practically for all of them, the solubility increases with temperature. For gases, without an exception, the solubility decreases with increased temperature. Does that make sense? Now imagine it is a particularly hot day and you go fishing on a lake. Where should be the hook with the bait be? Like, should it be close to surface or low? Low? Why? Why is fish there? The answer is on the board. It's hotter at the top, meaning less oxygen at the top. Oxygen is lower, and they find a layer of water that is most comfortable for them. Does that make sense?
Like every time it's like when you live in an apartment building, if you live toward the top of the building, it's always hotter there than
Yeah.
hot air rises.
Same idea. Yes. Go to a lake, like a smaller lake, in July, August, and go into deep water. There's a clear distinction. Top layer, maybe 1-2 feet, which is pretty warm, and then it drastically decreases. So that's the explanation. Okay. So this, a bottle of, if you will leave a can of Diet Coke in the car in the summer, it can explode. Why? Exactly. Carbon dioxide is being released from its dissolved condition into the can, expanding the can. Okay? And we already answered that question. I mean, if you will boil the entire lake, they're going to die. But generally speaking, there is enough. If it's a very shallow water, sure. But if it's a reasonably deep lake, they will find a space closer to the bottom. Okay. So this, I don't know, again, those of you who go into medical professions, no, not this. Hold on. This. Henry's law is quite important. It states that the solubility of gas in liquid is directly proportional to the pressure of that gas above the liquid. Okay? Which makes sense. Okay, if you increase, so what you have is here. So liquid, gas, right? Gas molecules go into the liquid and also leave it. If you increase the pressure of gas, there are more molecules that coming in than the ones that are coming out. And the concentration of gas in the liquid increases. Why this is important? I think we did have a conversation about the partial pressure of gases, remember? So when you go, remember, you go into the mountains, right? And the partial pressure of oxygen decreases. Does that make sense? Now, oxygen is transferred from alveoli in your lungs into the blood, and it's a classic, it follows the Henry's law. So if partial pressure of oxygen decreases, the amount of it that reaches the blood also decreases, which means the oxygenation starts falling down. Okay? Does that make sense? And that can be applied to any gas. Sounds good? Okay. So now we're going to talk about solubility rules for ionic compounds. So here's the thing. You apply these rules step by step. Quick question. Do you think there are exceptions from these rules? Yes. Otherwise, we wouldn't be able to determine compounds, ions like lithium or sodium or potassium, rubidium, whatever. There are some insoluble salts of them, but they are quite exotic and not in our, spectrum of interest. Okay, good? So, you have an ionic compound, all right? So first, you ask yourself, what is the cation? If it is one of these 7, which are very easy to remember, it is metals of the first group. Okay, you can see that. Plus ammonia. Okay? Seriously. Bless you. Francium is not... Francium costs like, I don't know, a military plane. This is why nobody really does any chemistry with francium. Now, let's say it is not, it is something else, some other cation, okay? Then you ask yourself, okay, what is about anions? If it's one of these 2, soluble. Clear? If it's one of these 3, soluble except for these cations. Okay? Does that make sense to you? So, let's say your compound, I'm just giving you an example, because I want to approach sulfate. Okay? So what is the cation? It's iron. Everybody agrees with that? Yes? Okay. Is it one of these 7 or 6? It is not. So now we need to address the anion part, okay? Is it this? It isn't. One of these 3? It is not, but it's a sulfate. So soluble, well, it's not one of these guys, so soluble. Am I making sense? No? Sure, yeah. Okay. nickel 2 chloride. Okay? One of these? No. One of these? Also no. One of these? Yes. Is nickel in the list? No. Nickel chloride is soluble in water. Does that logic make sense? Okay. Yeah. Barium sulfate, CT scan enhancer. So another example, Alicia, to your question. So why is this soluble? Because of potassium. Does that make sense? Why is this soluble? Because of sodium, because of nitrate. Okay, if you go back, this is your potassium, this is the nitrate. Making sense? Chlorides are generally soluble, but not lead 2 chloride, because it's lead, silver, and mercury 1. Okay? Sodium hydroxide, sodium. Aluminum phosphate. So I don't like this statement. No soluble ions. There are salts of aluminum that are soluble, but aluminum is not the leader among those soluble ions, and generally phosphates aren't soluble. Phosphates, sulfides aren't soluble. Okay? So, why they are insoluble? Well, cadmium 2 sulfide. Cadmium's not in the soluble list. Sulfide's not in the soluble list, right? Iron sulfide, iron 2 sulfide, same story. Now, lead 2 iodide, generally speaking, if you go back to this, iodides are soluble, but not when it's lead 2 iodide. Hydroxide and iron is not universally soluble, and nickel, is not universally soluble. Does reasoning make sense? Okay. So now we're going to talk about concentrations. And this is the definition. Okay? And I want to show you that you use concentrations almost practically every time you go grocery shopping. So, do you eat potatoes? Like from time to time? Yeah? If you buy them in bulk, it's like 5 pounds per bag. Right? This is nothing else than concentration. Am I making sense? It's the concentration of potatoes in one bag. So, sometimes, it's my guilty pleasure when students are struggling with concentration problems. I tell them, let's replace the solute with potatoes, with pounds of potatoes, and solvent with bag. And then it makes sense, like, what's the difference? There's no difference, okay? Try to imagine this concept rather than memorize it. So we're going to talk about 4 different methods for concentration measurement. Percent by mass, percent by volume, mass volume percent, and molarity. So what is the mass percent? And I want to highlight something. We take the amount of solute, the mass of solute, and divide it by the sum of mass of solute plus solvent. Okay? So it's a mass of a solution. So this is an example, right? Okay? What is the mass of solute? 8 grams, right? Right? What is the mass of solution? To form 50 grams, 50. So far, so good? Yeah. So, you divide it, get 16%. Let me ask you this. Can you make this solution not how it is shown here, but by measuring 8 grams of potassium chloride, 42 grams of water, and then mixing them? It's not a tricky question. Yeah, you can take 8 grams, add 42 grams, and get 50 grams. Okay? Sounds intuitive, doesn't it? It is absolutely correct. Don't worry, I'm setting up the trap for you. Okay? So that's the calculation of calculating the mass percent. So let's see what we've got here. So what do we have? We have 15 grams of, so mass of solute is what? 15.0 grams. Agreed? Mass of solution is what? What do I need to do to find the mass of the solution? Plus 235 grams gives us 250 grams. Okay, sounds good. So how do we find concentration? We divide 15 grams by 250, and that will give us, well, multiply by 100%, 6%. Okay? Am I making sense? Excellent. Can I skip this, how we solve this problem? There are 2 pages of... Okay, volume percent. So, same approach, but with different units. Usually, volume percent is used for liquids. Does that make sense? For instance, when you go to a liquor store and you see that it's 14, 15 volume percent, it means that 100 milliliters of the solution, wine, contains 14 milliliters of pure ethanol. Clear? So, same idea, right? So here's my question. Let's use liquor as an example, okay? So let's say vodka, 40% by volume, okay? Do you follow? Right? So, what does that mean? It means that 100 milliliters of vodka contains 40 milliliters of ethanol. Agreed? So, here's my question. Can you do this? to prepare this solution, 40 milliliters of ethanol plus 60 milliliters of water. So you think that if I mix 40 milliliters of ethanol and 60 milliliters of water, it will give me 100 milliliters of vodka? Not really. Let me explain why. Volumes are not necessarily additive. Do you understand what it means? If you mix, say, 50 milliliters of one fluid and 50 milliliters of another fluid, the final volume may not be 100. It can be smaller than that. Not by much. I mean, it's not going to be 50 plus 50 gives you 60, but it can be 50 plus 50 will give you 98 mils. Does that make sense? So, how would you approach the preparation of solution if you need a concentration by volume, if you can't use additive volumes? Go on. No. Like in the lab, what would you, because think about this. If you can use two radiated cylinders, right? You can measure 40 mils in one, 60 mils in another. Everybody agrees? Then you mix them in the beaker, but the final volume may not be 100. How do you make sure that the final volume of solution is 100 mils? Practically, like I'm giving you your glassware, a bottle of ethanol, a bottle of deionized. Go on.
Just add more
What do you mean?
until you get to the
Excellent.
amount that you
Yes. So you put, in general, you put 40 mils of alcohol in a graduated cylinder and then slowly add until it's 100 mils. This guarantees that the final volume is what you need. Okay, makes sense?
Exactly accurate anymore. Because like once you put, you're adding more of one, then like it's not a ratio anymore. Then you're just describing how much ethanol's in the bottle.
Exactly. Yes, you are absolutely correct. When we say it is a ratio, but it's a ratio, look at this. Milliliters of solute in 100 milliliters of the solution. Okay. $40 milliliters, 60 milliliters. Okay? Let me make it a little larger because otherwise I won't be able to modify it. So that's 40 ml. This is ethanol. Okay? This is 60 ml. This is water. Okay? Is this a ratio 40 to 60 in milliliters? Sure. Sure. Now, we add them together. What you may end up with is this. I am speedballing, okay? Do you follow my train of thought?
Yeah.
This is what can happen, potentially. That the final solution, final volume of a solution is less than the sum of the original, the volumes of components. It can happen. Does that make sense? Now, can you find the concentration of that solution? Yeah. You divide 40 by 90. My point, you can find the volume, or you can find a concentration, but if you need something different, you should take the approach that Zach proposed. Does that make sense? Okay, mass volume percent. That. And here's I want you to highlight something. You have to be careful with mass volume percent. When we talked about previous percentages, right? We were talking about milliliters dividing by milliliters. We were talking about grams divided by grams, right? Does that make sense? So your units would be the same and units would cancel each other out. Here, we only can use grams per ml. Because if we start changing willy-nilly one of the units, it will screw up all the concentrations. Am I making sense? So let's take a look how it works. So this mass percentage, what does that mean? Can you tell me? I'm going to give you a lead and then you'll continue, okay? 8.50 grams of sodium hydroxide in 100 grams of the solution. Make sense? What is this then? Okay, over 100 of what? Milliliters. Maybe I just didn't hear. What about this? 4.8 grams of hydrochloric acid per 100 milliliters. Good? Making sense? All right. Well, so yeah, the dilution of a solution, one of my favorite statements about, to a large extent, microbiology and safety in general. The solution to pollution is dilution. Okay? So, when we dilute something, we add water. Now, this is, again, I don't know. First of all, you're going to use dilutions in the nursing and DH classes because, drugs have to be diluted sometimes. When you add more water, the volume increases, the concentration decreases. Fair enough, right? Like you can make a very, very thick chicken stock and then dilute it if you need to. This is really important. The amount, the mass of solute remains the same. So, again, if you take 100 milliliters of vodka and dilute it to 200 milliliters, it still contains 40 milliliters of ethanol. Okay? So this is a very convenient way to calculate concentrations or the volumes of a solution when you dilute it. Because if you think about this, let's just play. Let's say you have concentration of 5 milliliters per 100 milliliters. Okay? 5%. Make sense? And the volume, I don't know, 10 ml. Okay? What if you dilute it to 20 milliliters? The concentration will go down, Does that make sense? But, so this shows you the amount of whatever you're working with in, I don't know, 100 mils of solution, right? So the amount is 5, it doesn't change. What changes is concentration. So let's play some learning checks. So we have 9% solution of sodium hydroxide. How should I write, and it's mass volume, concentration, how should I write the conversion factor? So what is the constant, how should I rewrite this 9%? Go on. 9 of what? But what? Units. Grams of sodium hydroxide over 100 what? It's okay. 100 milliliters of solution. I'm not going to write the word solution, okay? And what is the starting volume? It's in mils, right? Does that make sense to everybody? Now, this shows you how much sodium hydroxide we have in those 10 mils. Am I making sense? So, the volume that we want to dilute it to is 60 ml. Correct? So the question is, what is the concentration? And if you do all the math, the concentration will be 1.5 grams per 100 ml. Which amounts to 1.5% mass over volume. Does that make sense to everybody here? Now, I deliberately asked you to tell me what the conversion factors are, right? You don't have to do that. Let me show you. I mean, you don't have. You can write down the concentrations in percent. It's going to work just as well. Check this out. So, for instance, you can write down this. C1 V1 equals C2 V2. Okay? C1 is 9%. I'm not going to do all the significant figures. V1 is 10 ml. C2 is unknown, but V2 is 60 ml. Right? Then you just solve this, equality and get C2 being 1.5. Does that make sense to you?
So,
yes.
For the first way you went through it, what did you do? So, if you're doing 9,
Like all this crap?
it's like the first step you do is 9 divided by 100 times 10, and then what are you doing with in the second step with the 60 milliliters?
Let me move it over here. I can divide both sides of this equality by 60.
Oh, all right. So you're just dividing that.
And just, that's it. That it goes to C2 equals 9 grams of sodium hydroxide by 10 ml over 100 ml, 60 milliliters of solution.
Oh, all right.
Okay. Right?
Oh,
So-
so you're setting up like you set up like a cross multiple
Yep.
type of situation.
Yep. I'm gonna. Okay, so let's do it together again. All right, we will have to do a crash course because for some reason there is no molarity included. I don't think there is a molarity. So I will explain what molarity is. Molarity is moles of solute per 1,000 milliliter, or 1 liter, it's the same, okay? Make sense? Good? Questions so far? Kind of makes sense, right? And I don't know, I will leave it here. So there's another term, molality, not without R, but with L, which is moles of the solute per 1 kilogram of the solution. Good? Making sense? But in reality, it doesn't really matter because here's the deal. So this is what you start with, okay? So this is V1, this is C1. Everybody understands this? Then you dilute it to V2. So the question is, what is C2? So you can write down this. 0.180 liters multiplied by 0.600 molar concentration equals 0.540 liters multiplied by C2. Okay? So C2 is 0.180 liters multiplied by 0.600 moles per liter divided by 0.540 liters. Liters cancel each other out and you have 0.200 molar solution. A good check to sort of keep in mind, if the problem or question says, diluting, the answer, the concentration in the answer should be lower than the first concentration in the question. Does it make sense to you? Okay. So we're going to talk about these different types of mixtures from solutions to suspensions. So here are the properties of solutions that you must know. They are transparent, although they may be colored. They do not separate if you leave them alone. Does that make sense? So if you leave sodium chloride solution alone and presumably it's not evaporating, it's going to stay unchanged without crystals. So when it says contains small particles, pretty much molecules, okay? So you cannot really filter. With that being said, there is a reverse osmosis, which in some way can be considered a super fine filtration, and we're going to get back to this, okay? Now, colloids, medium-sized particles, cannot be filtered, so they will still go through a typical filter paper, but you can use semi-permeable membranes to separate these colloids from the rest of the solution. Okay? Does that make sense? So those are various examples of colloids. Okay? And I want to especially highlight this folks. Okay? And also this folks. So, or even this. Think from your personal experience. If you leave mayonnaise for a very long time, it will start separating. Like oil will start to rise to the top. It's not going to be completely separated into layers. Same story as with milk. Okay? What happens to fog eventually? Eventually, it will settle down on the ground, even if the temperature doesn't change, because gravity is there. Colloidal solutions like fog or shaving cream or dust or smoke will settle down. Am I making sense? To be fair, it's going to take a lot of time. Okay? Because there are colloidal solutions that were prepared sort of out of curiosity mid-20th century, like colloidal gold. They still, there's no separation. Okay? Because the gold particles are so small. Suspensions are non-uniform, and they will settle down. Okay? So you have to stir them. Again, chemists should not talk about the stuff that they don't really understand. Because I worked with platelets personally. It's going to take a while for platelets to settle down. But if we start talking about generally formed elements of the blood, red blood cells, white blood cells, yeah, they're going to separate eventually. Okay? So please be able to describe this rather, answering the questions. Like, what is the proper characteristic of a solution? It cannot be filtered, something like that. Okay? So this is a really good illustration of differences between the solution, the colloid, and the suspension. So if you have all three different types of mixtures in one beaker, when you run this mixture through the filter, only the elements of suspension will stay on the filter. Sounds reasonable? Both colloids and true solutes will pass through. But then you can put it, and forget about the reds, they shouldn't be here. Then you put a semi-permeable membrane, okay? This semi-permeable membrane, what's going to happen, and this illustration, the quality of illustration is not great. So imagine that this is the membrane, okay? On one side, you have solutions and colloids. Okay, does that make sense? We got rid of suspension. We filtered. So the true solutes will cross the membrane. The colloids will not be able to. Okay. Solute particles do not settle, but too large to pass through a membrane. What do we call it? A colloid. Yes. Now, osmosis. So one of the ways to understand, like, first of all, the water in the example of osmosis, as you can see here, it goes to the area with a greater solute concentration. Make sense? But Zach and I were talking about this on Monday. And this is an example that I want to use to make sense out of it. You all are familiar with diffusion, right? So diffusion is what?
From when particles go from an area of high concentration to low concentration.
Perfect. So just a little reminder. This is what diffusion is. Moving from high concentration to the low concentration. Right? So imagine we have two compartments. They're separated by semi-permeable membrane. And here you have, so red is solute. Okay. And blue is solvent. Which compartment has greater concentration of solutes? The right or the left? The right. Which compartment has greater concentration of solvent? The left. I should use a different one. More solvent. Okay. So solvent in this case will be moving from the area with its greater concentration to the area with its lower concentration, right? When we talk about solutions and use the term concentration, we apply it not to the solvent, but to the solute. So solvent moves into the area with a greater concentration of a solute. Okay? Now, osmotic pressure. Let's talk about the previous image, okay? That illustration that I drew here. So in this example, water moves from left to right. So at some point, the level in the left will be lower than the level in the right. Does that make sense to you? If you would, hear me out, if you would just sort of make a little hole in here, in which way would fluid go? From right to left, right? Good. But in our example of movement of solute, solvent goes from left to right, when the pressure exerted by that little part, that little thing here, when the pressure of that column is equivalent to can neutralize the movement of solvent to the right, we call it an osmotic pressure. Okay? Does that make sense?
So you're saying that at some point in time, that right side could still have more solutes in it?
They're going to the concentrations are going to become even.
So the pressure is when they are even?
So I know. So I want you to look at this image and try to think of it in dynamics. So in this example that I have on the screen here, right? This one. The solvent moves from left to right, which increases the level on the right. That increased level starts pushing solvent back, right? And if some solvent the concentration of solvent on the right will increase, but if the solvent returns, it will decrease. So there will be some equilibrium across the membrane when the osmotic pressure exerted by the left chamber is the same as hydrostatic pressure exerted by the right chamber. Without semi-permeable membrane, the concentrations would even out. But with membrane, they won't. There would be some balanced concentration. Now, it all sounds, and I do know that, it all sounds very, very, very boring. Okay? Here are a couple of examples how you can use that concept. So imagine the situation in which the concept of osmosis. So you have a situation. You have a cell, and the concentration of solutes in the cell, just a number, 10. The concentration of solutes outside of the cell is also 10. Will water move anywhere? No, there will be no net movement. We call it isotonic. Okay, environment. Now you put the same cell in the environment with a concentration of 1. So below than isotonic. So hypotonic, right? Where would water go? Inside the cell. What's going to happen to the cell if you start pumping it with water? Expand, right? Now, if a cell doesn't have a cell wall, like human cells, then this expansion will eventually break the cell. Make sense? There were cases of healthcare workers erroneously giving patients, instead of proper 0.9% sodium chloride IV fluid, distilled water, which diluted plasma, created hypotonic environment for red blood cells, and they exploded. Not only it reduced the delivery of oxygen to tissues, fragments of red blood cells, specifically heme, are toxic for liver, for kidneys, and the patient can go in acute liver failure. Go on.
Why would it go from the low concentration to high concentration? Because you put a 1 on the outside.
Yeah. Because it goes from low concentration of solutes. We talk about concentration of solutes. Okay? This hypotonic environment is the reason why small cells, like plant cells and bacterial cells, have a shape because of that pressure. Okay, does that make sense? Where does water go? 100 out, yes, it goes out of the cell in hypertonic environment. if I would, so when you buy salty food, like something, I don't know, like pickles or something like that, does it stay, I wouldn't say fresh, but edible, for a long period of time? Yeah. That's salt. Salt creates the environment that's super hypertonic for bacteria, and they just die. Okay, the water is sucked out of them. Making sense? Now I'm going to ask you my favorite question. The answer is kinda on the board. I mentioned the Dead Sea today already. Dead Sea is full of bacteria and archaea, full of those cells. And those cells feel absolutely fine in that brine. How so? One of my goals, what I try to do, you shouldn't be afraid of the questions like this. You should be able to go one step forward, like more than one step. So out of these three examples, isotonic, hypotonic, hypertonic, which situation is the best from the cellular standpoint? Isotonic. The tonicity, the relationships between the concentrations inside and outside, are they absolute or are they relative? So
is it the salt levels that are keeping the bacteria alive? Kind of like the salt keeps the pickles?
So think of it this way. If you take cell, right, and put it in the environment which has much greater salt concentration, I'm sorry, it's kind of hilarious. I'm getting some spam calls in the middle of the day from some Vanessa. If you put a bacteria in the environment in which salt concentration is super high, the only solution, no pun intended, for such cell is to maintain equally high concentration of solutes inside the cell. Does that make sense? If you will take those bacteria from the Dead Sea and put them in like regular environment, of course, they will explode. Okay? Reverse osmosis, yeah. So basically, it's a glorified molecular filtration. What you have is a semi-permeable membrane, okay? Now, if you think about this example, imagine that we add the plunger here, okay? And we start pushing on this solution. Am I making sense? It will force, this pressure will simply force the molecules of solvent to cross the membrane from right to left, because solutes can't do that. So what you end up with is a purified solvent. Okay? Few desalination plants to obtain pure water from the sea. So water can be a problem, right? What I'm asking you is this. Can you name the region in the world, not necessarily country, but the region in the world, which actively uses reverse osmosis to produce drinking water? How do you answer such a question? You look at what reverse osmosis is, and you start thinking, okay, if people use it to produce drinking water, they must not have enough drinking water. Which geographical areas in general do not have enough drinking water? Not tropical. Deserts. Deserts. Second question. If it requires a large amount of energy what does it translate into? A lot of what? The M word. Does energy come free? So if you want to use large amount of energy, you got to have a lot of money. I'm talking about humans. Money.
Oil, like the Middle East.
Exactly. Kuwait. And so Arabian kingdoms. Yeah. Gulf of Persia. This, as far as I know, Kuwait completely relies on desalination via reverse osmosis because they have like absurd amounts of oil. Okay. Now we talked about this isotonic solution. So 2 isotonic solutions that are used in the clinic: 5 gram per 100 milliliters glucose, or 0.9 grams of sodium chloride per 100 mils. That makes sense. Hypotonic, talked about this. In hypotonic solution, water flows into cells, okay, resulting in their expansion. Okay, that makes sense? Hypertonic solution, the water is sucked out of the cell because the concentration on the outside is way too high. Okay? I wanted to ask you something about hypotonic solution, and I can't remember what I wanted to ask. Oh, another lovely example. So, I don't know if you've heard about this. This was a real case. Some radio station in California organized a competition who can drink more water in a day. Huh?
Didn't the girl die?
Yeah.
From drinking?
6 gallons. 6 gallons in 24 hours. So if you consume 6 gallons of water in 24 hours, what's going to happen to the concentration of everything outside of your cells? You dilute it, right? So you create hypotonic solution in which cells have to exist. She had a neuronal swelling. Her neurons acquired so much water that it stopped functioning, and that's it.
Probably couldn't pee out the water as fast as she was taking it in.
Kidneys can't do that fast. Kidneys cannot process that much water.
Maybe Andre the Giant. I think I heard he could drink like 100 beers in a
Sure.
like
Yeah.
night.
But the beer, if you think beer is also a diuretic because it contains alcohol, not just because of the volume. So alcoholic drinks make you lose water, pretty much.
So
And go on.
is the difference between osmosis and reverse osmosis, is that kind of like, because osmosis would be like passive transport?
Yes.
Would reverse osmosis be like an artificial
Active transport. Absolutely. You have to use quite literally a pump of sorts to push the solvent to the area where it already is. Okay? Yeah. And I mean, I don't know what this case ended up with, but to be honest, perfect candidate for Darwin Prize. You're familiar with Darwin Prize? You're not familiar with Darwin Prize. Now, dialysis. We don't do dialysis as far as I remember. But so basically, this is the idea of semi-permeable membrane that is permeable not only to the solvent, but also to small solutes. Okay? Does that make sense? So for instance, from my research practice, one of the methods to precipitate proteins is salination. You add a shitload of salt and proteins get down, okay? They take with them a certain amount of salt. So when you resuspend them, you have proteins, solution of a protein, and too much salt. So what do? You put that solution into a dialysis bag. and put that dialysis bag into distilled water. The concentration of salt within the bag is greater than outside of it. So this yellow particles leave, leaving proteins behind. Not all of them leave, of course. Does that make sense? So in the dialysis machine, pretty much the idea is that smaller particles will be removed from the blood, okay? While larger particles, i.e. proteins, will stay in the blood. This is how kidneys work. Dialysis is essentially an artificial kidney.
Wouldn't that just be like a type of filtering? The dialysis machine would be like a filter to filter out the
Yes. The question is, what do we define as filtration? And let me explain. When you have small particles coming through a membrane, but large particles not coming through a membrane, we separate them by size. Technically, it is filtration. We don't call it filtration because then it will be confusing, because when we filter, we remove larger particles. Does that make sense to you all? Like, how fine is your filter? I used a filter with a diameter of a pore less than half a micron. Okay? You think that what you're filtering is transparent and true solution. No, there are tiny little particles that you can't see, but they will block that filter. So the question is, when do we stop? When it is a dialysis.
So filtering sounds like filtering's more of just like a general term, like
In chemistry, we reserve it for suspensions, pretty much. If we filter and there is something stuck on the filter, it was a suspension. Does that make sense? But it's separation by size. Just a quick reminder, 0.5% glucose, 5% glucose, 0.9% sodium chloride. So go. 2% sodium chloride, hypo or hypertonic? Say again? Hyper. 1% glucose. 0.5% sodium chloride. 5% glucose. ISO. Yes. Your cheat sheet. 5% glucose. What's going to happen to the cell? Nothing. 1% glucose. One percent glucose, hypo or hyper? Hypo. So cell is 5. Outside is 1. In a cell, so it's going to expand. 0.5 sodium chloride. Hypo, which means expand. 2% sodium chloride. Hypercrenation. Okay, that's solution, concept, map. Okay.